Actually, could we give another hand to the award winners? Those are fantastic talks. Congratulations, and thanks, Noah, for that wonderful perspective on mentors. I think all of us have benefited from that in our careers. Before I introduce the next speaker, I wanted to take just a moment to thank our science organizing committee. We had co-chairs this year. Amy Fagan is the first person I'd like to thank, so thank you, Amy. Clive Neal could not make it to this. He was very, very sorry about this, but as Amy pointed out earlier, when his wife Denise says you're going on vacation with me, that she is the one person that Clive listens to. So we're very sorry not to have Clive here. I'm going to quickly read off the names of the SOC here. Jess Barnes, Laura Bleacher, Dan Britt, Amy, of course, Tim Glotch, Jasper Helikas, George Kramer, Clive, of course, Deb Hurwitz Needham, Julianne Salmon, Andy Shaner, Bhairavi Shankar, and Jamie Soleil. So thank you all for all of your hard work in putting together what I know is going to be a really great program. Oh, yes. I'd like to, Yvonne's and my names are ex officio. Somehow we left Brad's name off. Brad always does a huge amount of work for this meeting. So thank you as always, Brad. So the first talk of this session is going to be given by Bill Bottke. And this is a new kind of a talk that we thought of. We thought it would be good to start our meetings with a review of some of the highlights from the last year. And I think you're going to be seeing the tip of the iceberg. This is perhaps 10 to the minus third or minus fourth of what he could talk about. I would love to hear him talk for 3 weeks straight, but anyway, and then I'd also like to say we're all familiar, of course, with invited and contributed talks. What I hope that Bill doesn't think of with regards to this talk is a new third category, and that's coerced. but I very much appreciate Bill for giving a talk on the last year of exploration science. So, Bill, please.
There's the thing. Okay. So I was asked to give a talk sort of reviewing the year in survey science, which, it's impossible unless you want to look at a bunch of bullet points on like how many papers we published and the rest. So I thought it'd be more interesting to actually try to give a science talk and try to give a flavor for things. So I asked all the PIs of the 9 teams that we have to send me some interesting slides of kind of a flavor of what they're doing. Not necessarily like their highlight from the year, but maybe something that was interesting or they liked or what have you. And since they're all sending me things, and I can't, maybe I can't be accused of plagiarism, but I thought I'd start off the talk with my word is my bond. So let's go from there. But beyond that, we have 9 science teams, and we also have a lot of international teams as well. I'm not going to cover the international teams in this talk. There just isn't enough time in 20 minutes. But I'll try to give you a flavor for some of the things we're working on. So I'm going to start with my group, which is the Institute of Science for Exploration Targets. So we're going to start sort of big picture, and we're going to kind of funnel our way down to really practical things we can do with the astronauts and the rest. And the thing to keep in mind with survey is one of the reasons it was invented is that seemed like it was a good idea to have a team of scientists that be working on all the places humans might go in the near future. So those are the moon, near-Earth asteroids, and Phobos and Deimos, ultimately leading up to Mars. But also it's because there's an idea that the exploration that we do on these worlds helps science, and science, of course, assists exploration. And so these are the kinds of things we're trying to get at. So really everything is relevant for these kinds of projects. So let's talk a little bit about planet formation. So this is some really interesting work that's being led by Hal Levison and Catherine Kredke, who right now is one of the survey postdocs. Okay, so they've been focusing on a particular aspect of planet formation, which we're very excited about, which is called pebble accretion. So if you don't know what pebble accretion is, I'll try to give you a quick rundown of this. So imagine you have an object, which is maybe a millimeter or a centimeter, or maybe even a decimeter, just flying in space, and it goes by something which is maybe the size of a protoplanet, maybe a moon-sized object, maybe a Mars-sized object. And what happens is this gets a little gravitational kick and not much happens to it, okay? So just traditionally when we're doing planet formation models, this is the kind of dynamics we do. But now think about yourself in a more realistic case. So you're in a solar nebula, okay? So now in a solar nebula, all of a sudden these small little particles can feel a headwind. They just feel a little bit of a little bit gets taken off their orbital energy, and so they can actually spiral into their doom. And so effectively what this means is that the accretion radius for bodies that get to a certain size can be very large. And in the modeling, it's really remarkable. You can go from something very small to huge in very short timescales. And so we implemented these versions of pebble accretion in a new code called LIPAD. Okay, and so what you're looking at here, this is planetary mass and Earth masses over here. This is two different simulations bolted together. So this is the inner solar system here. This is the outer solar system. They don't actually talk to one another. But what you're looking at is small pebble-sized objects growing up to be larger objects, protoplanetary objects, and then ultimately they start to grow into the planets. But there's some particular interesting aspects here. So you have to start to get Earth and moon-sized objects and the rest. But you'll notice that there's never a lot of mass in the outer part of the inner solar system, or there's not as much mass in the outer part of the outer solar system as well. Accretion kind of works from the inside out, and is the function of actually objects coming in the disk, actually evolving inward, and then accreting, and again, there's a preference for accreting from the inside out. Okay. So in the end, we end up with a system of planets, which looks pretty similar to what we have today. But one of the interesting aspects of this is if this is right, Mars very naturally has a smaller mass. This is something that's been frustrating modelers for quite some time. The asteroid belt is very naturally a low mass. It's not some big mass that we have to get rid of a lot of things. And then in the outer solar system, we end up with a couple extra ice giants, which is good for various reasons. But we also end up with a fairly healthy Kuiper belt, which allows us to make Plutos and all the rest. So this is now we'll see if this model ends up being right. It has a lot of interesting aspects. There's a lot of things to work on, but it's an exciting way forward and some new ideas, and it gets us thinking about all of our preconceived notions about how planet formation works. Okay. So now I'm going to jump to Dave Kring's group. He has the Center for Lunar Science and Exploration. And so this, the project I'm going to talk about here is sort of, in a sense, a test of some of the things I just showed you in the previous model. So in that model, you have giant protoplanets crashing together. And one of the reasons we think this is a reasonable thing to happen is that we have a moon. So in some cases in the model I just showed you, you have giant things crashing into the proto-Earth at the end game of planet formation. These things might be the size of Mars. They could possibly be in the size of like a half Earth or so. And they create a protolunar disk, and out of that grows the moon. Okay, so the moon forms here. But that may not be the end of accretion for the moon. The moon may still be hit by objects from time to time from the leftovers that are in that system. And interestingly enough, the very deep interior of the moon appears to have some signature of water. There may be some water abundance in the deep interior. And the question is, how did that water get there? And what's the source of that water? So there's lots of different ideas for this. We'll probably talk about some of this at this conference. But I'm going to focus on one particular aspect that was reported in this paper by Barnes et al. So what you see here are a lot of different water signatures we have for different substances across the solar system. Comets, meteorites, we have interplanetary dust particles, we have some different samples from Mars and the rest. And down here is basically the isotopic signature you get from deuterium versus standard mean ocean water. Okay? And so what they measured in this is basically this little rectangle shows where the lunar interior water signature is located. And so you can compare this visually to different substances we have in the solar system. And what this suggests is that, so here's ordinary chondrites, here's many different comets. There's only a few comets that really seem to have the right signature for the interior of the moon, but we have lots of carbonaceous material here. So this is CI, CMCOs. So a lot of our carbonaceous chondrites seem to actually fit this pretty well, but some things don't fit as well. And so ultimately this is telling us that if water is delivered to the moon by late accretion, and it would have to arrive, let's say, between when the moon formed about 4.5 billion years ago and about 4.35 billion years ago, it may have been delivered by impactors that had these kind of primitive carbonaceous chondrite signatures, or at least carbonaceous chondrite-like signatures, not necessarily ordinary chondrites or anything else. So that gives us something to think about in terms of forming the moon, in terms of what the moon tells us about planet formation. Okay. So the next group I'm going to jump to, and we're going to stay on sort of big picture questions for the moon, is Andy Rivkin's group. He runs the Volatiles, Regolith, and Thermal Investigations Consortium for the Exploration in Science. Don't these all just roll off the tongue? Isn't that nice? So, okay, so this is called the Vortices Group. All right, and so what I'm going to talk about is an interesting paper that came out by Matt Siegler not too long ago. So essentially, we using some of the different spacecraft we have, we can detect hydrogen signatures on the poles of the moon. And you just saw this in Dana Hurley's talk talking about water on the moon and the rest. But one of the things that's been found is there's actually a hydrogen signature that's offset from the pole. Now, in the poles, we have permanently shadowed regions. And so if you deliver water to the moon, it hops around and it may eventually find a cold trap. But this is not a cold trap today. So the question is, why is there any water signature there at all? Well, if there's something deeply embedded in the regolith, then maybe you could have that there. But still, how did it get there? And so Matt came up with an interesting proposition, and his team, is they suggested maybe this is a sort of a fossilized, permanently shadowed region. Maybe this used to be where the moon's pole was. Okay, so the idea of this is that in the past, the moon may have a spin axis which was slightly in a different location. So those were the original locations of the moon's poles. Okay, so then the question is, well, how did it get from where it was to where it is today? And what we know from the Grail team and other estimates is that the Procellarum region on the near side basically has a large concentration of radioactive elements, and they begin to heat up. As they heat up, that material becomes less dense. And the way things work in terms of moment of inertia, if you have a less dense region or you have a hole, holes want to move towards the pole, right? So as this tries to move towards the pole, it's actually shifting the lunar pole to where we see it is today. So basically, this fossilized pole tells us about the earliest history of the moon, how the moon heated up, and it also tells us something about what water was flying around the moon very early on in its history. So we can use all these things to really probe the deep history, or not just the deep history, but the ancient time history of the moon. So this is very exciting stuff. Okay, so let's jump to Carly Peters' team. She has the Evolution and Environment of Exploration Destinations Science and Engineering Synergism, so SEED, okay. And I'm going to talk about here some work that's been done by Jim Head, who just won a big award. Okay, so this is not quite an award-winning talk, but it's close, right? And Lionel Wilson. So they've been looking at some of the issues that concern basaltic volcanism on the moon. So here's a picture on the moon of many of the places where we see basaltic volcanism. Here you can see the pyroclastic deposits, and we even have some cryptomari over here. And the question is, when did this get here, and how precisely did this get here? So from a timing perspective, we think that substantial volcanism on the moon happened mostly between about 3 and 4 billion years ago. And then after that, it really tailed off, and there's probably not much going on for like the next couple of billion years or so. So, but the question is, why do we have this volcanism at this time? Well, a big clue as to why we might get it in certain locations and times has to do with the crust of the moon. So from Grail estimates, we now have a pretty good estimate of what the thickness of the crust is. So Grail is, so the thickness on the near side of the moon is much thinner than the far side. And so that's that's much better in terms of being able to get volcanism to the top. But even then, so what you have is you have early on the moon forms, it builds sort of a flotation crust made out of anorthosite, and then that has a certain thickness, but still you have this Mare basalt that has to get to the surface. So what they've been looking at is different modeling ways this could work. So they're actually having a basaltic source that melts, it has a certain amount of gas entrained, it starts actually kind of forcing its way or making a dike that kind of moves its way up. If the crust is too thick, the dike never makes it to the surface, it kind of stalls out. But if the crust is thin enough, it can make it to the surface. It begins to degas even more as it gets close to the surface, and all of a sudden you can get explosive volcanism. And so they can compare their model results to actually things we see on the moon in terms of venting and explosive eruptions. And they can just also look at dike intrusion and ultimately what you're getting from different kinds of basaltic flows and the rest. So what they're doing in this model is they're taking all the constraints we have from shields on the moon, cones, domes, pit craters, pyroclastic deposits, and the rest. They're comparing the results to what they get in their model, and then they're iterating to try to constrain their model to a great degree. So they just published 2 big papers on this, and I encourage you to read them, but I warn you, the abstract for each one of these papers is 2 pages long. So it's light reading, as you can tell. Okay. So I'm going to jump here to Bill Farrel's team. So now we're going to get to more of what might be helpful for the astronauts. What are some things we could do to help for their future missions? And so Bill's team is the dynamic response of environments at asteroids, the moons, and moons of Mars, or DREAM-2. Okay, so I'm going to show you this picture, and at first glance you'd say, oh, well, he's studying comets, right? So does anyone actually know what this is? It's kind of a comet. It's actually a waste dump of water from the ISS. So this is, what happens in the end. And so you think, well, why are we studying this, right? Well, it turns out there's an interesting issue that's sort of related to this, right? So imagine you have Orion that's going close to an asteroid. Okay, this is going to be a bad place for a wastewater dump, right? But beyond that, even if you don't do anything like that and you hold it, you cross your legs or whatever for months, okay, you still have the issue that basically the spacecraft itself is a little dirty in the sense that you're losing some degree of oxygen. Even the astronauts' spacesuits are losing some degree of oxygen. And what Bill and his team wanted to look at is how much of that oxygen will actually stick to the asteroid, assuming some kind of contamination from this. So what you're looking at here is a function of temperature. This is the amount of surface water you get per square meter or so. And these are the activation energies. So these are the sort of the stickiness energies you need to actually get yourself onto the asteroid. So at low temperatures, you actually require pretty low energies in order to become sticky. At much higher temperatures, it's much harder to get stuck to the body. And then you also have issues in terms of what the sample of the material is like. This material might be closer to, let's say, a highlands region on the moon in terms of what its surface properties is. Down here, you might have something closer to a Mare basalt. So ultimately, it's something we have to think about. If we're going to have astronauts interacting with asteroids, can we do it, but also avoid contamination so we're not changing the samples as we do interesting things with them? Okay. So let's jump to Tim Glotch's team. So Tim has the remote in situ and synchrotron studies for science and exploration, or RISE. Okay, so Tim actually gave me this interesting movie that was part of some of the work that his team's been doing. So this is actually an interesting lava flow that actually exists out in Hawaii. And so you would look at this and say, oh, well, that's a great shot of a helicopter flying over taking video. Well, it's actually not. It turns out they wanted to use drones to actually do remote sensing of this lava flow, but they weren't allowed because drones aren't allowed in the national park in Hawaii, so they had to use kites, right? So this is all imagery taken from kites, but the point here is that they're not only doing remote sensing, so they're trying to get topography of this layer, but they're also trying to get all the optical properties of this lava flow as well. And so from this, they're trying to say things about the nature of the lava flow and the rest. But in a sense, what you're trying to do here is a preliminary study. So you track as well as possible everything you can learn about that lava flow. And then ultimately, you find the most interesting regions, and you're going to send astronauts in there to explore those regions. And so the question is, what's the best way to get at regions so humans can do the most efficient things possible when they go explore those flows? These are some of the things that his group is trying to get at. And in related ways, I chose this purposely because then it leads very well into Jen Helden's team. Her team is field investigations to enable solar system science and exploration, or FINESS. So her team is really based on this idea of how can we help the astronauts do the best field work possible when they go to some remote site. Okay. So she actually this summer, and she's been doing this for several years, but they did a deployment in the summer at a place in Idaho called Craters of the Moon. Okay, and this is a place where some of the Apollo astronauts went long ago. And so what she's trying to do here is actually, if for some of the young people in the audience, when the Apollo astronauts went to the moon, they had a mission control, but they also had a team of scientists in the back room that would provide input to the astronauts. But the scientists, are jibber-jab. They like to talk all the time, and they can't be like filling the astronauts' ears with useless information, right? So there has to be a procedure as to how they provide information to the astronauts, how the information goes back and forth, what's the best way to get the most interesting samples, but then let the astronauts do their jobs. So here are their astronauts for Jen's team. So they're preparing for the EVA, and you can see the backpacks here. There's a mission control with some scientists in this, also trying to run the whole operation. There's actually a back room of scientists which are controlling things and trying to say, well, this rock looks interesting, maybe this is a better sample and such. They're controlling where their positions are or tracking them very carefully in terms of a monitoring system. They've actually done remote sensing of the region prior to the investigation, so that way they could try to compare what the astronauts are seeing with their eyes with what they're actually getting from remote sensing and the rest. And then one of the regions that's kind of interesting on this is they're actually exploring a lava tube that's near there. And we thought we'd throw this in. This is actually a case where I think one of the scientists here set up a tripod and did LiDAR radar of this lava tube. And so you can imagine on the moon, one of the great things about lava tubes on the moon is it might be great places for a future base of operations because you can hide from the deadly radiation that we have. You can imagine building something down there and the astronauts coming out and doing things, but you want to explore that lava tube to some depth. It could be that a LiDAR scan of that lava tube from the astronauts' positioning material might actually be a good way to explore some of these things. So there's a lot of neat things here. And at the same time, this same kind of research is telling you about the viscosity of the lavas and everything else that you have during this site. Okay, so now we're going to jump to Mihai Harani's team. This is the Institute for the Modeling of Plasma, Atmospheres, and Cosmic Dust, or IMPACT. And so what Mihai's been doing, so they've been doing a lot of things, but they've been actually looking at this almost 50-year-old mystery dealing with some of the early missions to the moon. So this is an image from the Surveyor spacecraft, which landed on the moon. This is very close to sunset. So keep in mind, you don't have an atmosphere. So there is no, when it's light and it's dark and it's all pretty quick, right? So what's interesting is after it was dark, just as sunset happened, they still found some lighted material that was illuminated. And the interpretation of this is dust that's been elevated to about a meter off the ground, and it's actually still catching a little bit of sunlight. Now, they didn't see this at sunrise because they didn't have cameras positioned there, but sunset, they consistently saw this. So the question is, what are they seeing? And the interpretation is they're getting some kind of electrostatic dust levitation from this. And so they've been investigating this in the laboratory to try to figure out what this means. So they're actually, they've created a sample simulation, and they've looked at laying down dust, but they've also looked at the porosity that's below the surface as well. And what they find that the charging of the dust, if you put UV light on it or if you put a plasma in it, it's not just the charging of the surface material, but it's actually this charging you also get in the porous material below the surface, which ultimately can lead to the levitation you want. And so when they did this, and so I did, again, lab experiments, you start to see stuff hop around. So here's some example of some small little micron-sized dust particles hopping around. And over time, you start to get a lot of these things hopping out of the hole and doing all sorts of interesting things. And they think this explanation for what's going on explains what we're seeing on this. And this is something important if we're going to have astronauts living on the moon. They have to worry about, how does the dust environment change over time? Is this something they need to worry about for equipment or for themselves? Or, what's really going on with this? Okay. And then finally, I'm going to end with Dan Britt's team. Dan Britt has the Center for Lunar and Asteroid Surface Science, or CLASS. So Dan's been doing a couple interesting things. So one of the things he's been doing is preparing asteroid simulates. So all of us want to be able to work with primitive carbonaceous chondrites, because that's actually a very common substance that we have with near-Earth asteroids. The problem is that things like orgeat are remarkably rare, and people get very mad at you if you want to go to orgeat and say, I'm going to smash it into a bunch of bits and use it for my own purposes, right? So instead of getting the real orgeat, we get Dan to make orgeat. So Dan goes to all this work to try to make simulants that are reasonably close to orgeat. But it also, so we want this for our different studies. But there's also, we want to get at to how this material might behave in microgravity studies. So one of the other things they've done is they've taken tubes filled with different kinds of material, some of it from simulants that Dan's made, other just particle-sized studies. These are tubes that are just, I think they're about, they're fairly small, just a few inches by a few inches or so, and they put them on the ISS. And what they've done is they want to perform a controlled experiment. And so what they do is they just let the astronauts do whatever they're doing, closing doors, opening doors. All this produces a small amount of perturbations on the tubes, and then they watch how the tubes slowly mix over time in this micro-G environment, trying to mimic as best as possible how an asteroid materials might mix. And ultimately, you're trying to get coefficients of restitution. You're trying to really understand the properties well enough so if we actually interact with an asteroid, we know what the surface properties are going to be like, and we can handle them as far as how they interact with their equipment, how they're going to interact with spacesuits and everything else. So it's pretty interesting. And so I'll just end with this, saying that Survey is about to have out a new can. It may come out any day, I'm not sure. But we're looking for a few more teams to join us. And so if you're interested, please sign up and write a really big proposal. So that's it. Thank you.
So you probably noticed we're running behind. Let's take time for perhaps one question if someone has a burning question. That's right.
I'll show it to the PI. That's okay.
All right.